The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone, and welcome to the Weeks 3 to 4 S2S Webinar Series. Just a few things before we get started with our presentation today. We do have a website on VLab. You can just go to vlab.noaa.gov and search Weeks 3 to 4, and this is the first item that does pop up. On our website, you can register for each month's presentation. Also, if you missed any or are interested in watching them again, we have all of our past webinars listed on our website, and we have links to the YouTube recordings for them as well and some presentation slides. Also, if you are interested in giving a presentation during this webinar series, you can fill out a Google form here and our staff will schedule with you to make that happen. We have openings, I believe, starting for the summer around May timeframe. So please, if you have anything to present, a 15 to 25-minute talk, and go ahead and fill it out and we can schedule you. And if you want notifications for registration, please fill out a Google form here and we'll get you on our mailing list. Also today, if you have any questions during the presentation, please put them on our Google document. And then at the end, our two presenters can respond to them if we have time, and also can continue the discussion afterwards. This link is on our VLab website, on the registration email, on the calendar invite, and also I will put the link in the chat window right now. If you have any questions, please type them in there. Okay, now I will pass. We have a joint presentation today by Dr. Zhang and Dr. Wang, and I will pass them over to them to introduce you and get started with our presentation. Thank you.
Can you hear me?
Yes.
Okay, thank you, Karen. I would like to thank everyone for participating in this seminar, webinar. This is a joint presentation between two NOAA teams. One is based on Pacific Marine Environmental Laboratory in Seattle. The other is based on NSAP CPC in Silver Spring, in Maryland, in College Park, I have to say. So the team members are listed here. There was a project that is supported by CPO, WPO, Climate Testbed. The whole idea of this project is to transform a developed diagnostic tool, large-scale precipitation tracking method that has been used in research to identify individual MGO events and to study the MGO behavior in terms of its precipitation. To transfer this to real-time monitoring, and hopefully eventually it will be used in operation to assess the unified forecast system of NOAA. Next slide, please. So this presentation will include two parts. I'll give the first part in which I will introduce the large-scale precipitation or LPT methods, and I will give you a brief demonstration how this method is used to develop skill scores to measure the CFS forecast scale of MGO using CFS reforecast. Then Wanqiu Wang will take over to cover the main part of this presentation to demonstrate how this method is used in real time to monitor the forecast scale at a CPC. Next one, please. Okay, so I'm going to describe briefly the methodology. First of all, this method was developed using a train precipitation analysis. And then the method was also applied to other satellite estimate of precipitation, iMerge and CMORPH. So in this presentation, I will start with the train, and then the comparison between observations and NOAA models is basically based on CMORPH. Next one, please. So this method has been well described in a number of publications, mainly by Kearns and Chen. And the one I recommend you is this one showing at the bottom, is published in 2019. This includes several steps. The first is preparation of data, satellite observations of precipitation, because this is for larger scale precipitation tracking. So first of all, we're going to apply some very simple filtering using accumulated rain for 3 days. That's essentially is filtering in time, and apply a spatial smoother using a Gaussian smoothing with a standard deviation of 2.5 degrees. That's basically space filtering. So these two methods guarantee that we focus on larger scale precipitation characteristics. Then a very tough decision is we have to decide what the precipitation threshold we are going to track. So they decide, the current Chen decided using 12 millimeter per day as a threshold. So I have to emphasize that these three parameters, 3-day cumulative rain, 2.5 Gaussian standard deviation, and the 12 millimeter per day threshold are all kind of subjectively decided, because there's no purely scientific objective way to decide this. Just as when you apply it to any time filtering, you have to decide the beginning and end, right? And there's no clear cut where you want to draw the line. So this is the same thing. But once you decide on these parameters, all the rest will be completely objective. So those thresholds will not change. So let me make that clear. Next one, please. Okay, so the first step to tracking is to identify large scale precipitation object. We call it LPO. So that's just individual location of large scale precipitation, and it satisfies the criteria of rainfall within that area is larger than 12 millimeter per day. So you can see in the map here, the red arrows point to some of those larger areas. Some can be a little bit small, some can be very large, but they all satisfy one condition, that the averaged rainfall is larger than 12 millimeter per day. The second one is to see whether there's overlapping of the tracked LPO in consecutive time. And so to the right, you can see those blue dots are overlapping to each other, and that means they have a high potential. They belong to the same objective, it's just moving in space and time, right? So the criteria here is they overlap consecutively at least for 7 days. And that we'll call LPT, the tracked features. Then if the tracked features move consistently eastward, then we call it MGO. If it is propagated eastward longer than 10 days, then we'll call it MGO. So that's the basic method for MGO tracking. Next one, please. So this animation just basically show you what happened. On the top is individual LPO, the tracked individual larger scale features, and the bottom is just the consecutive features. And you can see in this particular case, things are moving consistently and eastward for quite a few times. And so in this case, this is an MGO event. This tracking has an advantage that it can track the motion in all directions, zonal direction, meridional direction, east to west, north south. This doesn't matter. It can track. The biggest challenge is, again, the threshold. So I told you that for TRIM, we use 12 meters per second. Then you go to other satellite observations, they have a different mean precipitation. You go to the models, they have a precipitation bias. So the threshold would not, one single threshold would not apply. So the way we deal with this is we use the mean precipitation as a factor to rescale the threshold. So those thresholds are determined based on the difference between their mean precipitation. Next one. Okay, so the product of this tracking is the following. First, you can decide the individual MGO events, where it starts, beginning point, and where it ends, the end point. And between the start and end point, you'll have the longevity, how long an event lasts. You have the range of propagation, MGO propagation in the zonal direction, and you can have the scales, the spatial scale that determines how large area aerial coverage would be, and the strength that will be the volumetric rainfall within the tracked area. So those are the product of this tracking method. Next one, please. Yeah, continue, please. Okay, so how do we use this method to develop the skill score for a CFS forecast? So in this case, we treat MGO as rare event, and we borrow the commonly used ski scores for rare precipitation events. So on the table to the right, you can see there are 4 scenarios. So we divide the entire Indo-Pacific area into three regions: the Indian Ocean to the west, Maritime Continent in the middle, and the Western Pacific to the east. And then we identify MGO events week by week. So in the table to the right, you can see if there is an MGO event in observations, and the model also forecasts that events, we call it a hit. And if there is MGO events in observation, but the model did not forecast, we call it a miss. On the other hand, if there is no MGO events in observations, but the model forecasts an event, it's a false alarm. And the last one is there's no MGO events in both observations and model forecast. So it's called a true miss negative. So the map to the left just demonstrate how you judge in terms of these 4 scenarios. And you can see that the time is going from bottom up, and the axis is longitude. You can the red is forecast, blue is observations. So you can see over Indian Ocean at the beginning, this particular forecast pretty well hit the observed MGO events. And then later on, the observed MGO event propagated eastward, but the forecast events, some kind of stall, did not propagate. So it's become separate. In that case, it will be a miss. And you go to the upper part of the figure, you can see the 2 events are separate. The forecast events stays in the Indian Ocean. The observed events started from Indian Ocean, propagate into the Pacific. Even though the timing are perfect, the location are completely separate. In that case, it will be false alarm in the Indian Ocean and miss over the Maritime Continent and Western Pacific. Next, please. So based on these 4 scenarios, you can again borrow the literature borrow the commonly used matrix from the literature. So in this bullets, we'll list several of them. And we found only the bottom one, the equitable threat scores and Hadgas scale scores, are most useful. So here, the curves in the bottom demonstrate, just to give you an example, the blue color is for December, January, February. The red is for June, July, August, and black is for whole year. And immediately, first thing you can see that is using this particular score, these 2 scores, CFS does not have any skills in JJA in terms of predicting MGO precipitation. You see the red line is pretty much 0 or negative after week 1. When it's negative, that means your forecast even worse than random selection. But in DJF, the blue curve, you can see it has some score, and beyond 1 week, 2 weeks, or even 3 weeks, but definitely not beyond 3 weeks. Beyond 3 weeks, it's be very close to 0. And this is different from what you would get using RMM, because RMM measure the global large-scale circulation, and this is a local precipitation. So you would expect the forecast scale will be lower if you want to forecast precipitation than circulation. And Wanqiu will give you a more detailed description of how this score can be used in real-time monitoring and skill assessment. Next one, please. Okay, so then the question you can ask is if the model has a hit, the forecast the MGO events, how well it reproduces the property of that particular MGO events. So by property, we can judge using duration, using longitudinal propagation range, using scales, that's the maximum error coverage of precipitation, or use the strength volumetric range. So, and in the bottom, the scatter diagram just show you the example over Indian Ocean, over Maritime Continent, on the Western Pacific. I don't want to go to details, but I can tell you 2 things that are very interesting. One is if you focus on the Indian Ocean to the left and the upper left panel duration, and you can find CFS overestimate the duration over Indian Ocean, right? And you move to the right panel, that's the longitudinal propagation, you find that the CFS underestimate the longitudinal propagation. And you can make your judgment through other maps. But most interesting thing is the color dot, the color. The color represents the lead time. Blue is short lead time, red is long lead time. There's no dependence of those scattered on lead time. This tells you that the errors in predicting individual MGO properties is not a part of error growth of the prediction. The errors start at a very early lead time. That just indicate that those prediction errors is inherent in the model capability to reproduce larger scale precipitation characteristics. So I'll stop here, and Wanqiu will continue to introduce you how this method is applied to real time. Wanqiu, please.
Okay, Karen, could you go to the next slide, please? Okay, so my name is Wanqiu. We work at CPC, and we work with Chidong's group to test this method for MGO monitoring and forecasting. So first thing we did is we transfer the code to CPC workstation and tested it. The language used for this package is Python, so it's very easy for us to use. And then the goal is to test this for real-time forecast. So we start with one run per day from 0Z forecast and the 6-hourly output. And we use observed precipitation analysis from CMORPH, which is our analysis. And we developed the experimental page to update this. The update started May 2020. So we have a page to display this. So we don't need to click on this. So we can just go to the next slide, which shows you how this page looks like. So basically we have 2 parts. The one part is the latest forecast. We have the tracking. You can see the LPT tracking on the very left panel. And then we have a forecast of spatial distribution of precipitation together with the LPT areas that is black, that is indicated by the black circles. And then on the right, we have verification. So for verification, we have tracking. So that is a comparison between the forecast and see more precipitation analysis. And then we also have a spatial map for every 7 days. So we have 7-day, 14-day, and so on. So that's basically what we have so far. So obviously we still need to further improve this for other statistics and for better use of the tool. So going to the next slide, please. So so one thing we have done is a comparison with other MGO indices. We look at the comparison in time series of the amplitude of real-time multivariate MGO index and OIR MGO index, and compare them with LPT. So one question we want to ask is, okay, we have RMM and we have OMI, we have other MGO indices. Why do we need another one, LPT? So as we will see, there's no single MGO index that is describe the whole picture of the MGO. One major feature of this LPT is it provides local precipitation or convection information. So we'll compare the time series of these three indices. Then we will look at the comparison for individual cases for observation and for forecast. So next slide, please. Okay, here's a time series of the amplitude for RMM and OMI and LPT. So we know RMM used winds and convection to calculate the index, and it uses the global modes, and it doesn't. Interesting, filtering is not applied. And for OMI is convection only, and it's also global modes. And before the calculation, interesting, filtering was applied. And RPT is basically local information. It's convection, precipitation, and no interesting filtering. So here we have a comparison for the past 5 or 6 years, starting 2017. We have the black curve for RMM, so and the red curve for OMI, and RPT is plotted in blue. We see different types of periods. The first type are periods over reasonable correspondence among the three indices. For example, 2017, February, January, and 2018, February, January, January, February. So for those two periods, we see a good correspondence, and all indices show the relatively strong amplitude. And the second type is the periods of good correspondence between RMM and OMI. Both use global modes. And one example is 2019 November, which is the second row, somewhere in the middle. We see a good match between OMI and RMM. And the third type is the period that does not show good match. So for example, the lower panel, let's see, January, I think this is 2021, sorry, yeah. 2021 January or February, we see a strong RMM, which is in black, and there's a very weak OMI signal and no RPT signal here. And the other two periods of this mismatch is, one is 2017 October, where we see a strong RMM and weak OMI and a very brief period of LPT when the RMI index started to develop. And another period is 2019 February, March. So where we see a short RMM, and we see a longer period for LPT. So the message here is that this indices provide complementary information. So, and we do need convection information, especially for the local information, to give a good picture of MGL. So let's go to the next slide. So here's one example of comparison. This is for October 5th to 22nd, 2017. The left panel is a phase diagram, and we have the black is RMM, the commonly used MGO index. We see a relatively strong MGO amplitude with RMM for relatively long, like 3 weeks or so. And we see the OMI is relatively weaker, and we see like a stronger signal during the second half or so, something like October 14 or so and after. So which is weaker than the RMM. And for LPT, which is a local signal, we only see the strong signal at the beginning of the RMM development. That is October 5th to 8th or so. So we also have the amplitude comparison, the upper right panel showing the evolution. Basically, it gives the same information. And the other panel on the right is the LPT areas, which shows the strong signal during a very short period. Okay, let's go to the next one. This is another period, or another event for February, late February to March 2019. Here we see in the late February and early March, we see strong MGO signal in all three indices. And then we see the RPT continue to develop in Western Pacific, but OMI and RMM signals becomes very weak. If we look at the lower right panel, that is the RPT areas. There's a jump from March 8th to March 9th. So the area jumped from Eastern Indian Ocean to Western Pacific, just 1 day apart. So obviously this is not a continuous propagation. So this is like two separate episodes. And what's interesting is there's no OMI and RMM signal corresponding to the period after March 9th. So that's kind of interesting. So let's look at the next slide. So now this is a forecast of RMM, which is showing on the left panel. So we have the forecast from CFS from different initial dates. The black is the observation, and the green is forecast from October 5th, 2017. Obviously, this is not good forecast. The amplitude is very weak from October 5th. And forecast after that, like a forecast from October 10th, 15th, and 20th, are all good. or forecast capture the observed amplitude. What this indicates is that before the convection developed in the Indian Ocean, the model was not able to forecast the evolution of the RMM index. And after that, the model did a very good job in the forecast. So next one, please. So, oh, sorry, go back. Okay, good. This is another, the evaluation for another period. Again, RMM on the left. We see this time the forecast from all initial dates showing here are very good, including forecasts from February 24th, March 1st, March 6th, and the 11th. All of them capture the observed evolution. This is very, very interesting. And in particular, the forecast from CFS from March 11th is also weak, which is very good forecast for the weak MGO amplitude. The reason I said this is good is because actually, if you look at convection, after that, it's already strong in the Western Pacific. The model successfully captured the observed weak amplitude of MGO. So that's another good forecast too. Okay, let's go to the next one. So this is the forecast of RPT for this period. We have observed tracking that is in black, and the forecast are in colors. We have two forecasts here. One was initialized from February 19th, 2019. And the other one is initialized from February 24th, 2019. So for the forecast from February 19th, the model captured the tracking in the Indian Ocean, which is in green. And also model captured the development in Western Pacific. However, this one occurred too early compared to observation. So the forecast started February 21st, and it's way too early. So that's like a false alarm, basically. And the other forecast was initialized from February 24th, which is very good for the for the Western Pacific. That is, and also very good timing compared to observation. However, the model produced another false alarm to the east of data line. So that's a bad one. Okay, so let's move to the next slide. Okay, then we also did some evaluation of the scale for LPT and RMM. So for RMM, we calculated anomaly correlation coefficient and RMS error and Hadkey scale score, and for LPT, we calculate the Hadkey scale score. So let's move to the next slide. So we first look at the RMM prediction scale. This has been used by many people. Here we look at the bivariate anomaly correlation coefficient, which is left panel. We look at the forecast from using 1 member, 4 members, and 16 members. Obviously, the scale increased with the ensemble size, and the model forecast scale 0.5 is at about day 15, which is somewhat shorter than that in the published results, which all show that CFS model has a scale of 20 days or 21 days. The reason is probably because here we use R1, INSEP real analysis 1 for the calculation. Actually, we didn't calculate this. We just downloaded it from Australian website. So that's probably the reason. The published results for the CFS evaluation or based on recalculated index using consistent reanalysis. So that's probably the reason. And the left panel is RMS error. And we see that the model forecast skill is at about 20 days or 15 to 20 days. If we measure this using 1.414 as the threshold. All right, that is for RMM. Let's go to the next one, which is now for Haddock skill score. We just want to calculate this for consistency check. The scale is obviously lower than the RMM scale. Than the correlation, anomaly correlation scale. And we see that the scale is relatively lower for maritime continent, which is upper right panel, compared to that for Indian Ocean, which is upper left, and the Western Pacific, which is lower left. And we also see a slight increase of the scale with the ensemble size. It's not as clear as that for anomaly correlation. So that is RMM. Let's go to the next slide. This is also the evaluation for Haddock skill score, but now we look at first we look at the weekly scale rather than daily, and we compare the scale for different 2 periods. One is before May 2020, and the other is after May 2020. So clearly the scale depends on the period. So that means if we want to do a comparison, we have to use the same period for different method. Yeah, the rest will be the same. The scale increase, slightly increase with ensemble size, and maritime continent scale is lower than Indian Ocean and Western Pacific. Okay, now let's go to the next slide for LPT. So we did a similar calculation for LPT, and we have 3 panels here, which is for Indian Ocean, that is upper left, and maritime continent, that is upper right, and the Western Pacific, which is lower left. Each panel we have 3 curves. Blue is for winter season, November to April, and the red is for summer season, which is May to October, and black is for full year. Obviously, there's a big seasonal contrast, as Chidong has shown. And again, we see the scale is higher is higher in highest in Western Pacific, in the lower left for winter season, and is lowest for maritime continent, which is upper right. I think that is what we see from this slide. Okay, let's go to the next one. As Chidong discussed a few minutes ago, one important parameter for the LPT is the precipitation threshold. So we because of that, we look at the dependence of the scale on the threshold. Starting from control setting, we tested the criteria using lower threshold, that is control -2, to higher threshold up to control +3. And we tested this for different regions. And what we found is indeed using alternative threshold values may lead to a better forecast scale. And such a dependence depend on lead time. So that means we need to use different values for different lead time. So for example, for Indian Ocean, the upper left, using control plus 2 millimeter per day, produce the best scale. And for week 4, using using a control plus 3 gives the best forecast scale. And overall, for Indian Ocean and for Western Pacific, which are left panels, we want to use a higher criteria. However, for maritime continent, a lower criteria value produced a better scale score. So the reason for this is the model's bias is lead time dependent and also region dependent. So as we will see in the next slide. So next one, please. So here we are looking at the a scatter plot of precipitation for for 3 different regions. So the top row is for Indian Ocean, and the middle row is for maritime continent, and the lower row is for Western Pacific. And the left column is for day 4, and the center column is for day 11, and the red column is for day 18. So let's look at the top row. The bias is the pattern is similar from day 4 to day 11 and day 18, although the bias amplitude changes. And basically, we see that for stronger amplitude, the model produced larger amplitude of rainfall for Indian Ocean. And we see the same feature for Western Pacific, which is the bottom row. That is the model amplitude is relatively larger than observed. And however, if we look at the middle row, the model tends to produce a smaller amplitude compared to the observation for larger precipitating range. So this means we need a lead time and amplitude dependent rainfall bias correction before the LPT processing. So that is hopefully this bias correction will lead to a better scale for LPT forecast. So next slide. So that is basically what we have got so far. So there are a few things that need to be done in the future to give a to further improve the use of this tool. The first thing is bias correction. As we just talked about, we need a bias correction. We can use like PDF correction or quantile mapping or even pattern correction. And then the second thing is again we have been using just one single member forecast for this. The CFS produces 16 daily forecast runs each day, so we can use that with the with a 16 member ensemble. We can produce the tracking from each member, and we can also calculate tracking density, and we can produce like probability forecast. And another thing we can add is we have, in addition to CFS, we have GAPS 12, which which may also have a good scale for MGO forecast if we use multimodal ensemble. And then another thing we want to improve is the real-time display. We can add phase diagrams. We can add tracking area evolution. So there may be more things to do, but here are the things we think that will be helpful to improve the product. So now let's go to the last slide. So in summary, we have demonstrated the use of LPT for real-time monitoring and forecast. This method has been tested at CPC. Our evaluation indicates that a precipitation bias correction is required for better use of this method. And we also, our evaluation also indicate that further improvement is required, including the use of additional members and models for real-time application. So that's what we have for today. Thank you.
All right, thank you both. We do have a couple of questions on the discussion document. I will share that now so everyone can see. Okay. Okay, the first question we have, is there any particular reason to use CFS to monitor MJO? Why does CPC set up GEFs for 35 days, which is running once per day with 31 members and 31 reforecasts as well? I'm sure GFS should have better skills than CFS.
I can take this one.
Okay.
Yeah, the reason we started with CFS is when we started this project, CFS was the latest model that produced a better MGO forecast, and the GEFS 12 or GEFS is obviously recently implemented. We did see that GEFS 12 scale is better than CFS, and yeah, as I just indicated, adding GFS GEFs will likely improve the scale, and also will change the way we make the forecast from single member to multi-members and multi-models. Can I go to the next one?
Yep, next one. Are times where RMM, OMI, LPT agree associated with a particular flavor of the MJO?
Yeah, that we don't know. We need to look into this more to find this out. My guess is there are different periods that they agree more than other periods. So Chidong, do you have any?
Yeah, my take is the following. The major difference between LPT and RMM OMI is the spatial scale and coverage. Both RMM and OMI depends on the global EOF analysis. So the index basically tells you globally in the tropics how MJO is perceived. RMM emphasize on circulation, OMI emphasize on OLR, but they are all global scale. LPT is different, it's focused on basin scale. So when you track LPT, it does not go beyond one basin because the MGO precipitation scale is a basin scale. And when you propagate, it's a different story. That's the major difference. So when they agree, what does that mean? When they agree, that means with a particular precipitation pattern of the MGO, it set up a well-behaved circulation. That's the difference between LPT and RMM, association between LPT and RMM. Okay, so if there is a larger scale precipitation and give you a global scale pattern of RMM, these two will match. LPT and OMI is same thing. If somehow LPT is in somewhere and it does not project on the global EOF number 1, number 2, it will not match OMI. And for example, if the LPT small scale is relatively small, for example, and maybe there's somewhere else the precipitation exists somewhere else. But anyway, if that particular LPT and precipitation does not project to global EOF, the two will not match. So the match is pretty much depend on how local precipitation is related to global circulation, is related to global EOF of OIR. That's how I see it.
Okay, good. Next question. Are the precipitation thresholds the same for the CFS and OBS?
No. I think, yeah, sorry, we didn't indicate this clearly. In Chidong's part, I think they use 11 millimeter per day for observation. I think that's probably because the use of different observational data set. And for CFS, I think a threshold of 13 millimeter per day was used. And in the plot, in the calculation for our plot on CPC side, we use 12 millimeter per day for observation and 15 millimeter per day for CFS. So it's still not well established values. So that is why we did a lot of tests, and we wanted to, yeah, the best way is probably to do bias correction first.
Yeah, in this case, there's a reason why the threshold should not be the same between models and observations, because a model has systematic bias in precipitation. So if a model systematically produces more precipitation, you can imagine the tracking will give you different results if you use the same threshold, right? So, on this notes, we think the best way probably is to use the mean precipitation as a scalar to rescale the threshold, and we are testing it right now. And so just remove a little bit arbitrary. So you can have a observed threshold, and then you compare the mean precipitation between observations and model forecast, and use that ratio to rescale the threshold. I think that might be a way to go. And another thing I need to point out is because the forecast bias is not static, it changes with the lead time. So no matter if you select the one single threshold, then it will affect your forecast. Wanqiu already showed you, right? If your goal is to get the best score, you use a different threshold at different lead time, but they may not be the practice you want to follow. So this is why the bias correction is needed, because the precipitation bias change with the forecast lead time.
Okay, and then one last question. How is LPT plotted on a phase diagram?
You want to take this one, Chidong?
I think that's your question.
Okay. Okay. For phase diagram plotting, we need two values. One is amplitude, the other is location. So that is what we want. So the LPT package has the output of where the LPT is and how big it is. So the location is fine. Yeah, we know the longitude. We just plot that. We can find the longitude in a circle, along the circle. And for amplitude, this is discussed in the paper by Brandon and Shui. We have amplitude, so the amplitude is rescaled such that it has a good match or reasonable match with RMM and other MGO index. So anyway, so we just rescale the amplitude and then make it more consistent with RMM, then plot it using the amplitude and the location. Thank you.
All right, thank you, Chidong and Wanqiu. We appreciate you presenting today. And thank you to everyone who joined us for the webinar. Please join us next month on March 7th, where we have our next presentations, and they will be on developing and verifying a subseasonal outlook tool for extratropical storminess and a deep learning filter for intraseasonal variability of the tropics, and that's March 7th. Again, thanks everyone for joining us today. If you have any more questions, please type them on the document and we can get them to the presenters for answers. Thank you.
Thank you, Karen.
Thank you, Karen. Thank you, everybody. Bye.
Bye.